A stand is being used to prop up a portable solar panel. It consists of a support that is hinged to the panel near the top and an adjustable strap joining the panel to the support near the bottom. By adjusting the length of the strap, the angle between the panel and the ground can be changed. The dimensions are as follows. AB is 30, AD is 5, CB is 5, CF is 22, EF is 4. Now I've drawn out triangle CAF. Note that the strap DE does not have to be parallel to the ground. It might look like it's parallel to the ground here, but we're not told that it is, so we can't assume that it is. We want angle alpha to be 60 degrees. We want to find the distance between D and E. Now, what I will do is start by getting this angle here. We can use the sine rule to get this angle. And once we know this angle, we can then find the angle up here. And by looking at triangle CDE and using the sides of length 20 and 18 and this angle, we can use the cosine rule to find this side. Anyway, we can't get this angle directly, but we can get this angle down here from the sine rule. So now we're looking at triangle CAF. So we see if we call this side little a, then this angle here will be capital A in the triangle CAF. So we know that A over sine of capital A equals B over sine B. We take B to be this distance here, 18 plus 4, which is 22. So capital B must be 60 degrees. Small b and capital B are opposite each other. Now we want sine of A, so we just rearrange the sine rule. Sine A over A equals sine B over B. Multiply across by A, and we get sine of A equals A sine B over B. So we plug in the values. Well, A is 20 plus 5, which is 25. Angle B is 60 degrees, that's what we want. Small b is 18 plus 4, which is 22. So I followed the convention of using the letter A to stand for the missing quantity. In this case, we're using capital A for the missing angle. So this is the value we get for sine of A. We want the inverse sine of this quantity. I will write down this angle to 2 decimal places. It is 79.78. Now we can get this angle up here. So we add this onto 60 and we take from 180. 3 angles add to 180, so to 2 decimal place, the angle at the top is 40.22. Now let's consider the blue triangle, CDE. We are interested in DE. We can't use the sine rule, we don't have enough information. We have 2 sides and an angle in between, so we use the cosine rule. We call the side that we're looking for small a, that's the convention that I use. So if this is small a, then this angle here is capital A. And we call the other 2 sides B and C. We call one of them B, it doesn't matter which. Let's call this one B and this one C. So we write down the cosine rule and we plug in the values. So we have 20 squared plus 18 squared minus 2 times 20 times 18 times the cos of the angle in between sides B and C. We get a squared equals 174.22911, etc. Now we want a, so we have to get the square root of this number. So if I put this to the power of a half, we get 13.199. Now I will write this down to 1 decimal place. Actually, it's equivalent to writing it down to 3 decimal places, so 13.2 is very accurate. And distances are in centimeters. Find the maximum possible value of alpha, correct to the nearest degree. So we can move this strap in and out through the hole here at E, and we can vary this angle alpha. Now, we can imagine the support being perpendicular to the ground. So here's the support. It should be clear that angle AFC, which is this angle here, has to be less than or equal to 90 degrees. If this angle is more than 90 degrees, then the support will look like this. And I'm sure that that's an unstable configuration, so we need to consider the situation, the extreme situation for angle AFC. That is when angle AFC is 90 degrees. Let's see what alpha is. So we see that the sine of alpha in this right angle triangle is opposite over hypotenuse. We can use our trigonometric ratios here because we're dealing with a right angle triangle. So we have to get 22 over 25, which is 0.88, get the inverse sine of it. To the nearest degree, this is 62 degrees. Notice here that when alpha is 62 degrees, C, the distance of C above the ground is 22 centimeters. This is the maximum distance of C above the ground, this distance here. We could imagine moving the support CF so that it is at an angle that is less than 90 degrees to the ground. That will result in the point C moving closer to the ground. So for example, if C is here, so this would be the picture for some other alpha, which is less than 62 degrees. We can see that this distance is less than 22. So the sine of alpha will be actually less than 22 over 25, which means that alpha will be less than 62 degrees. So this must be the position for the solar panel that maximizes alpha, the position where C is at its maximum distance above the ground, so that the sine of alpha has its maximum value of 22 over 25. The sine of alpha is always going to be some number over 25. So we need to maximize this number on top. So when the support is vertical, we do maximize the sine of alpha, which in turn means we maximize the value of alpha.